Well, it's Dr. Know-It-All. I am super, super happy to be with, yet again, Scott Walter, who is a factory simulation and robotics expert, and also Gary Schneider, who is co-founder and CEO of Train Station LLC and a biomechanicist and a bioastronautics expert. We're going to talk a lot about robots, stuff that I don't know that well, which is the mechanical aspect, things like arms, legs, and weird chicken legs and all sorts of fun things like that. So yeah, let's take it away.
Yeah, I will. So it's really good to have Gary back with us. He's been on a couple other episodes, and Gary is a font of knowledge when it comes to how biomechanics works and everything else. So I've learned a lot from Gary, and so some of the things that I've got right, credit him. Some of the things I got wrong, now credit me. Okay. And the reason why we invited Gary on here is we did a video a week ago where the premise of that video was, does Optimus have too many joints? And so I went through this argument of detailing, so, well, what's the minimum number you really need? Why doesn't it just have 3 joints? And why did it have these others? And it really was like, why does it have such a big butt? Why are the motors there? And of course, it turns out the most interesting thing is they designed 3 different actuators, which are rotary. And the biggest ones are in the butt and nowhere else. And they seem to be where the motion is the motion you least need. It's like, that's not as important to walking the leg. So if you haven't seen that video, you might want to go through there, because we weren't able to get Gary scheduled in there. So now we would like his take on that and what he thinks we got right and what we got wrong. So take it away, Gary.
Yeah, I mean, I loved the video. It was definitely fun to see you guys rolling with the booty. I'm glad the Optimus booty has now become like this thing that everyone's talking about right now. So it's kind of hilarious that that's stuck with it. So, but I definitely think what you guys touched on with the 3 biggest actuators and the hips being really important from a humanoid robotics perspective. It matches, I guess, a lot of our anatomy, a lot of our function in creating this, bipedal creature that can also lift things up in front of it and can produce lots of power and potentially be a fast-moving creature over long distances, let's say. I think some of the interesting, maybe before I go on too much of a global tangent, I think the thing that stuck out, and I'd be curious to run through with you, Scott, too, is that we had talked about hip abduction. That was the first thing I think I remembered from your video as well, and whether or not it's necessary, and whether or not Teslabot really needs to be able, and for those folks,
for people who can't see, because I'm trying this gallery view thing, but Scott, if you talk, Scott.
Okay, I'll be talking and you can kind of see it right now. This is what hip abduction would be. It's basically, I guess, as a yoga pose, like, people do this all the time. I don't know if they call it abduction or what they call that, or if they just call doing it splits.
And then abduction is the outward going one, and the adduction is the one that goes inward. Is that correct?
Yep.
Okay.
Yep.
Yeah.
You think of like abduct, like aliens abduct you away, goes away from the midline, and then adduct, you're adding it back to the midline. Classic anatomy class trick. Hopefully you can retain that forever.
There we go.
That never leaves.
Here is the takeaway from today's video is now you know that abducted is like abduction. There you go.
Yeah. Now for the next one. This is rotating and supinating, or is this rotation?
So if it's occurring at the femur, then we would probably refer that as internal and external rotation of the femur. Yep.
Okay. Internal, external. Okay, there's that. Now, these are the 2 motions that we were sort of saying, you don't really need that to walk forward.
Yep.
And so maybe you need it to pivot, but you don't really need a big motor there, do you? Now, it turns out the second biggest motor is used to do this motion here, the rotation. Mm-hmm. All right. So for those of you at home, they're not quite seeing it. It's more or less like if you keep your legs straight and you make your toes point in different directions, rolling about that. So there is one motor right in there for being able to do it. And then there's the abduction, which are the real big buttocks motors, the maximum gluteus that just goes way out and in. And that's the biggest one. And the one thing I sort of forgot to mention, the last one, is there's probably a reason why that's a bigger motor for this direction than this one. And it comes down to moment of inertia. So when you were doing the rotation here, you're rotating along an axis which goes straight down your leg, and most of your mass is concentrated along that axis, which means from the standpoint of rotational inertia, there's very little, almost none there. The other thing that's kind of key and interesting is it's also centered along there, which means when you rotate it, it's not out of balance. So we all know what happens in the washing machine when you have a load imbalance and you're rotating about it, and then everything just kind of goes flying around. When you look at this motion here, first of all, your rotary axis is in this direction and all your mass is concentrated farther and farther away. So you need more torque just to be able to get the same angular speed that you would in this direction or acceleration. So that's one reason it needs to be a little bit bigger. And then the other thing, if you think about it, there is no mass on the other side of this when you rotate it to balance that out. And so when you're throwing up the leg like this, there's going to be a reaction like your washing machine, which means the torso has to react. And again, I'm like, this torso motion, that's a joke. I mean, that's not the one we do the most. You know, it's really bending forward or twisting, yet the biggest motor is for this. And that probably, and Gary is shaking his head in the yes way, not this way. He's agreeing that that could be a reason why, is that when you do this, you have to be able to counter that as well. Otherwise, you're going to fall over.
Yep. And I think the biggest thing, and you and I have talked about this a couple of times, I think in different videos, but I think the key word you said there too is that generation of acceleration from that hip and that plane of motion in particular. And that it's not even so much about peak force, but time to force and the ability to generate that peak force quickly in reaction to whatever the sensory motor control unit of the Optimus is experiencing at that time. And definitely, rotation is important in fluidity of movement. And I think rotation's hot in biomechanics right now because it's been the missing link, right? But like even if we were to look at even just like our kinematic graphs for patients day to day, there's not a massive contribution of force production or power out of the transverse plane or the rotational plane in gait. It is a lot of sagittal plane motion, but I do think that one of the things I like about the Optimus design and incorporating rotation is it has that option for improved fluidity of motion. And I think the lateral side bending and the ability to, let's say, like pull your body back to that equilibrium from that one side is definitely, I think, why they made that larger motor there. The cool thing about having the rotational component of the femur, though, is the small, fine movements that make something look smooth. So it may be not necessary to factory function, but I think in interacting with it, maybe even an efficiency problem over the long term, it could be really beneficial. And I think Scott and I even, when we were talking on Twitter, the example we used was watching Optimus walk up to the workstation versus watching Digit walk up to the workstation. And just by having that internal rotation available at the hip, you can see Optimus kind of has a really smart alignment to its workstation. It can pivot smoothly into its workstation around the foot. And it takes less time, it's less steps overall, just in that little sequence. And you have to watch something like a Digit move and align itself with its workstation. It ends up looking kind of like that side step clunky adjustment. And it's a really small step. But I do wonder if over time, and lots of sequences and lots of task actions, if that adds up from an efficiency standpoint too.
Okay. That's actually really cool. And for those who haven't seen the Optimus video, again, you can watch, I'll link the other video that we did at the end of this one, but it kind of goes, it does that little knock knee thing. As it turns, it kind of like rotates its knees inward like this.
Yeah.
And Scott's going to demonstrate.
Yeah. So walking, you would be kind of straight like this. And suddenly when it needed to turn, it decided to sort of put one leg like this so it could pivot it around. And its knees just kind of came in. And that's what was resulting in this movement here.
Yeah. Right. Yeah. But I mean, it doesn't look quite human because it's not the way we would turn, because we have a little more flexibility in our hip areas, more degrees of freedom. But anyway, but it is an effective way of it realigning itself on a new path.
Right.
Yeah.
And we'll see other bipedals have that.
We're going to talk about Digit in the second half of this video. But Digit is by Agile Labs. Is that the name of the company? Anyway,
Agility Robotics.
Agility Robotics. Sorry. But that's like an alternative in a really, really cool humanoid robot that we're going to look at. But there's some.
Be careful. It's not a humanoid robot.
Human-centric, right? Yeah.
Human-centric robot. Yes. We could argue, and actually, all right, let's table that.
We'll get into that later. We'll get into that later.
Okay. Right. Continuing with Optimus, though. Thank you. Sorry, Gary, take it away.
I'm trying to think. Oh, and then I guess some of the other stuff you guys were talking about was counter rotation and whether or not like what's happening there and whether or not that's necessary, and the torso being really still. I think a lot of that comes from that coordinated arm swing with the pelvis. And so the way it's keeping the torso still and counterbalancing it is the nice addition of the massive arm swinging back and forth. I'd be curious to see what that looks like. And again, I think a lot of it comes back to velocity. The walking gait is much better. The toe off is, to me, a really important part of making that extension and fluid movement a lot better, and maybe taking some of the strain off of those hip actuators, those really powerful hip actuators. But even just the way that the hardware is set up at the knee, it's biased towards that hip needing to do a lot of the work, keeping that bow shape and the slightly bent knee,
Okay, good. Because I want you to see a couple of images here. Is that I'm just going to go ahead and do a share right now, John. And these are some images we've probably already seen before. So this is a close-up of Optimus in the Investor Day video. And remember, we were kind of speculating a little bit about what's going on here behind the belt buckle. There is no charge port behind there. I think we've confirmed that. And I think I found out also looking at some other things why it's not there. But what I want to bring to Gary's attention is look at this pelvic girdle that's here. So we basically have 3 attachment points, which are hard to see, but we're going to see in a second. But look how thick this casting here is. If it's a casting or it's a machine, that's pretty thick right up there, where you have these actuators attached through a point here, and it turns out a point behind the buckle. And this is what caused me to then bring my attention to this slide here, which was one of the CAD images they had of the girdle. And you can see they've already in here decided to make space for the badge to go on there. And then back behind here, this is not where charge port is, but that is the connection with the motor behind here in there as well. But look how deep that recess is there. Now, maybe it's from the CAD, maybe they dropped the bolts or whatever that are connecting there. But to me, it seems pretty thick. And I'm wondering if it's solid all the way through or behind it, because they showed in some of the earlier ones where they milled it out to make it look more like an aerospace kind of surface where you have the ribbing that's in there. So it seems like they need a certain amount of torsional stiffness here, because you are. So remember, this motor is going straight down, but that axis going way back there is going back to the big boy there. There's another one there. There's another one there. And it may be when all 3 of those are kind of actuating together, it's applying a lot of rigidity or a lot of torsion there. But what kind of confuses me a little bit is, at first I want to give a shout out to Future Now, who tweeted these at us the other day. And as a result of these tweets, we were finally able to figure out where the charging port is. As we can see, it's right here in the back. And there is actually a control module underneath here. So it makes sense that this is already connected to the battery pack in one way or another.
I'm sorry. If this is where it ends up on the production model, there is going to be no.
Yes. And notice this is rather heart-shaped here as well. An upside down heart, and then there's the port, and it goes into this control module. But what I really want you to see here, is that in the back, the plate back here is not as thick as it is on the other side. So here's like another close-up on there, and you can see that this is probably just some plastic housing that snaps over it so you don't see where the attachment points are. But that is nowhere near as thick as it is in the front. And I'm wondering if all the loading is somehow being transferred to the front. And this, so we can see right there in the back how it's attached. So what are your thoughts?
At first glance, I don't have a great answer for the front versus back thing just yet. I think I need to think on that for a little bit. But at least as far as the rigidity of the, if you want to call it pelvis or the base of the torso structure or something like that, it makes a lot of sense. I think from the closed chain movements you expect it to perform. So if it's just lifting its leg off the ground and putting it back down, or if I'm an open chain like a shoulder and I just have to kind of worry about the mass of that arm that I'm moving it down and maybe a tool, I don't think you have to worry about the frame, the torsion going back into the frame so much. But I do wonder if things like where the foot is planted on the ground and there's maybe a counter mass, or it has to move the entire mass of the structure around that closed chain planted foot, if that was putting too much strain on the chassis before, it makes a lot of sense.
Right. Right. I mean, you get a triangular structure, which should be nice and solid and everything else. So that was perplexing to see how thick that is. And it's like, are they hiding something in there? Is what I was wondering at first. Like, maybe there's some stuff behind there that they just need to put some electronics or something else.
I think structural makes the most, it seems to me, just from looking at the motors and also where the plugins are, that it wouldn't need a whole lot of space necessarily for the wiring or the other infra. I think that mass is actually just there to support the closed chain torsion from that large motor set in the hips. I would guess. Yeah.
Yeah.
I don't think that there's a lot stored there.
Right.
And
again,
of course,
going,
Scott, as obviously as we talked about, we're talking about the 3 largest motors in the whole body are connected to that.
Right.
That's so
that one thing.
If anything needs structural rigidity, it's going to be the center of mass.
It's going to be right there. Right.
Yeah.
Yeah.
And again, from this, we can see this is an attachment point. That is not where the plug is going to go. I was expecting to find, well, there'd be another big hole here for the plug if it was going there. But now we found out from an actual photograph where it is.
You know, it's funny, John, you said center of mass. And after you said, I do wonder if, because at least right now, I couldn't think of, just from the arrangement of the motors, and I also can't fully see what's going on as to why there'd be like a torsion restraint is to the front needing more than the back. Could be the arrangement of motors, but I also do wonder if it's to do with center mass. They're somehow putting the larger chunk of machine metal in front.
I'm of course analogizing for human beings, of course, because our center of mass is right about there. But you know, with the batteries up in the torso, it could, I don't know, it could be slightly higher on that, but it's going to be close to where the center of mass is.
Do you think the batteries in the dorsal computer weigh more than the motors, or roughly, or what do you think is the greater mass?
Well, that's why I said it's just hard to know. If anything, it could be slightly higher, but it also, it's got to be somewhere right in that ballpark there, you know. So
I've got something in here that I can calculate where it is. Just give me a minute or two.
So you
Scott's like, I'll have an exact answer for you in 3 seconds.
I know that's leave it to Scott to actually have spreadsheeted out the entire thing, how much everything weighs.
Oh my gosh, yeah. No,
nice.
Okay, so what we have here is that they tell us the mass of all the servos, and we know there's 28 of them. And so you can look at this breakdown right here. And the battery based on that is about 10 kilograms.
Okay.
So that's the battery pack. These are all guesses that are in purple. So I have no idea how much the head weighs. I'm guessing the computer weighs about that much. And then just whatever the rest of the structure is kind of a guess. And that gets me pretty close to the actual 125 pounds that they said it should be.
Interesting.
So, you know, it could be off a little bit. That would be a little bit more, but yeah, total number of servos.
But I mean, in a way, it actually kind of looks like
servos weigh about 40.
It looks like about the way a human, because, you know, our legs are very, very heavy because they're muscles. So they balance out with the torso, which is the biggest sort of bulk of our body. So, interesting.
Yeah. And I do wonder then if the battery is that heavy and it's located upper torso, if they are adding that little bit of mass in front at the pelvis to bring the center of mass down, because I can imagine you don't want that center of mass too high. And Optimus, that's why the legs are so long relative to the.
Could be. Yeah, the battery is about 10 compared, so the legs, I guess, are coming about. Yeah, so that's because I also want to find out how much the torso. I guess I'm guessing is around. Okay, so the torso. Those are the torso motors. So if you add that in the battery, you're getting close to 16 kilograms. For the whole torso, maybe, and then the head on top of that. So you might be getting close to 20 right around there. And then the legs are only about 10 each, and the arms are about 5 kilograms. So again,
it's pretty top heavy.
Yeah. Well, I mean, and that also could be one of the reasons why it tends to walk with bent knees all the time.
Bent knees, right? So,
got to lower that center of mass. But of course, also with the arms hanging down, when they're not up, then that lowers the center of mass too, because some of the weight is down here. So but certainly it's going to be somewhere in that middle area of the body, close to where that girdle is.
I don't think I realized it would be this top heavy.
Yeah, well, that's what I was thinking about, because of the fact that the batteries and all of the components up here, they weigh quite a bit. But I mean, it's not just the center of mass; it's also the center of force. Maybe, I don't know. You know, it's the place where the pressure. The place with the largest amount of main heavy things are going to be moved from, if that makes sense, because you're moving the whole upper body and each leg, and those are the heaviest components.
When you look at here, all the action is happening right through here.
Right.
The torso servos are right up in there. You've got both of those legs and everything else that the pelvis is trying to do. That's a lot of activity happening right there. And you're right. You want to centralize that somehow, and maybe they don't want it so much in the back, but whatever they can do to push to the front. Which might be why the belt buckle is there. Because to me, it's like that belt buckle's got a little bit of a mass. And and actually, if you look at the price of this belt buckle, on the Tesla shop, it's probably worth more than Optimus, you know?
Yeah.
It's like, that's the most expensive part right there, probably.
Right.
That's like $100 right there. I'm sure
somewhere.
they can make the servos for less. So
don't tell my wife that, because she doesn't know how much it cost when I bought that back there. So yeah. So
yeah, it makes sense they would move that center of pressure forward too. Like I think just even by that center of pressure moving forward, they're offloading the torsion to the back motors, the posterior chain, if you will, giving it that slight forward bend. Yeah, it makes a lot of sense.
okay, so you didn't have any outstanding criticisms of that video?
Nothing. Yeah, other than okay, so other than the question of whether or not I think Optimus needs hip abduction, and if I think it's still beneficial to have that, I'm in the camp it is, and I think there was conversation between that from the other robot we'll talk about, stuff like that. But I think from a takeaway from that segment, I definitely still think that there's value to it, and I think a lot of it has to do, again, going back to the biologist in me that I think keeps trying to drive this home of you know, goal and task directs needs, and the needs then direct the emergent behavior that comes from it, and what will actually happen with the movement of behaviors available to the robot. I think that the long-term goal of Elon Musk and the long-term vision of colonization is in consideration of the design criteria still with that. And my use case for that is egress and ingress operations. So it's really difficult, even if you could get that a different bipedal type leg structure to sink down really low and fold well and reach into like low shelves and stuff like that. I think having the option to not only reduce the overall size profile, but then move laterally or rotationally through complex environments is the advantage, and having the range of motion to the hip and the ability to support it through those ranges is really important. So yeah. So let me stop the sharing right now. So yeah, my feeling also is that the hip was very important, that when it's walking, that its torso and everything is able to sort of stay rigidly aligned that way. Yeah. And then you don't want to have too much of this back and forth. So if you're carrying something like a tray that's going to have soup on it or something like that, when you're walking, you don't want the tray doing this. So the whole idea is you need that hip to be able to make sure everything stays nice and level. You're not shaking things around. Yeah. So without it, then that movement is going to be back and forth. And it's one thing if you're just carrying a box and you don't care, but it's something else if you actually have something that is delicate or could be spilled very easily. Right. Well, and there's two aspects to it, because the one is the stability aspect. I think you covered really well in the video, and that's, you know, being able to maintain that level platform by having that access of force and range of motion in the lateral plane. But I think the other side of it that they're not there yet, but I think will be interesting to see emerge is you know, deep range of motion and having enough force and being able to generate enough torque in a deeper range of motion with a really odd lever arm and do that effectively. So I think the more complex the movement will get, the more value you'll see in the hip, for sure. Yeah.
So even though interestingly enough, even though we've been talking a lot about how this version of Optimus is the MVP or minimum viable product, it looks like they are intending to future-proof it to some extent, because it could certainly walk with a lot less going on in the middle section. But if it's going to be able to do squats and go and pick up boxes low down and do more complex tasks, it's going to require more of that. So they are thinking forward at least some period into the future. Yeah. Okay. Should we switch over to talking about Digit versus Optimus? Because Digit's kind of awesome.
Yeah, absolutely.
It's pretty sweet. Yeah, it's
Digit's
sweet. It is.
So what I think I want to do here is show, this is called Digit Tries to Get Out of Work. And I think I'll just go ahead and show this video. We can react to it. And then there's another video that gets into more details about what's going on. But let me go ahead and... Hey,
have you seen that new Chit Chat GPT update?
No, I haven't. What does it do?
Oh, it's awesome. You don't even have to work anymore.
Oh, cool.
All right. So there you go. That is very, very, cute and adorable. So, oh my goodness. I've got the advertisements running now. Okay. So yeah. So what do you want to say about that? That's, I mean,
we don't see all of the robot there. So there's some other videos where we can see all of it.
Yeah. And I can go ahead and share the screen and just cut the sound off and we can talk our way through that. But anyway, and that was very cute. Like, and it's got a little hand in that version because you see in the other ones
the Lego hand. Yeah.
Awesome.
Now the first thing is, John, is like sometimes you're not quite sure whether something's a vacuum cleaner or a robot. Okay. So you might be a bit confused on whether this is a humanoid robot or not. Okay.
I've learned my lesson. Human.
No, actually I learned my lesson because I would have said this is definitely a humanoid robot. So it's not me, the Optimus fanboy, which is saying, well, if it's not Optimus, it can't be a humanoid robot. No. It's actually them saying that. They are saying it's human-centric or it's a bipedal robot. But I would argue in many ways that it seems pretty humanoid to me. But it is really well engineered on every front for the design aims of what they want to do, how they went through it. They understand a lot. This robot is already safe. It's a cobot right out of the box. Right. No doubt about it. And we'll talk a little bit about the legs, and we'll also talk about where Digit gets its name, because it doesn't get its name from where you think it gets it from.
Right.
Yeah.
But also I think it's worth exploring what a cobot is, of course, for people who don't know. So we can, if I just kind of like, so this is Digit in a factory situation, and you can see this is what I was talking about. It has little fist hands instead of grippers.
Which could be for this kind of task is probably good enough.
Yeah.
You don't necessarily have to have anything more than that.
Exactly. So
and it's a cobot because we have these nice kind of plastic housings around there. We don't have any sharp edges.
Right.
I mean, if you look at that, that's an industrial robot, which looks like it's going to hurt you.
Right.
Versus all those things. You don't get anywhere near those things. They're going to bump into you and they're going to hurt. They're rock solid. But if you're going to have a human-centric bot, you've got to make sure it's not going to hurt you. Follow the cobotic standards that are in there. No pinch points, making sure fingers aren't going to get caught anywhere.
So Scott, for these guys, for example, these are an in-between state. I think they're used a lot at Amazon warehouses and stuff.
Yes.
They look like a Roomba vacuum cleaner, basically.
The Kiva robots.
Actual robots.
Yes. They are mobile robots. So it used to be that, robots we always thought as an arm, and these things came around, and usually we would call them like an autonomous vehicle or something like that. But then the term mobile robot kind of came into the terminology that you'd be using. So they are very clever in that they're able to navigate around on their own. And as you can see, they can just get underneath things really well and pick them up. So they are an amazing solution for warehousing because they can literally get rid of aisleways. Because if you look at a warehouse, you say, all that wasted space, that is just an aisleway just to be able to get to stuff. And it's like, don't worry about it. We just kind of move them around as we need.
Right. Yeah. So, but of course, as they talk about in the video itself, the problem is that this is a very limited use case, and you have to design the factory for these robots, including the shelves. The shelves themselves have to be designed for the robots.
So basically there were two types. There were mobile robots that just kind of picked things up without any sort of manipulator or arm on them. And then there were the arms that were bolted to the ground. And now it's like, can we try to combine the two together?
Yeah.
Right.
Yes. Right. Yes. And now they started out trying to solve the walking problem first and not worrying about the rest of it, which is also very clever. So his background has been like for years in the university, figuring out how to come up with some sort of walking structure and then really clean sheet looking at the whole thing. Right. And they say, we're not trying to be humanoid because we're not trying to steal the design from a human. We'll be inspired by biology, but we're not going to let it guide us or force us to do something. And then as they designed up the tree, when they went from just having the legs, I think they might be showing you here, they actually had basically like an ostrich running around with no torso or anything else. When it came time to put that on there, they said, well, what's the best design? And they tried everything to not design a torso. Right. And in the end, it was like, well, it turns out the torso is the best. And that is great that they arrived at that conclusion. And they said, we don't want that. But in the end, that's what we have to have. And in many ways, they redesigned the human body in subtle ways that we've been able to pick up on here.
Right. And I think this image is not perfect, but it shows, let's
Yes.
see if I can find a little bit.
And they even didn't want to have a head on there because they didn't want it to look too human-like. They really,
Right.
they want it to be, there's this fine line between non-threatening and friendly. The problem is if it's friendly, people are going to want to go up and hug it,
Right.
And they're kind of afraid of the children are going to start hugging the robot because the adults are doing it, they're setting the bad example. So they're trying to do something to make sure you're not going to be scared of it, but at the same time, realize it's a machine. And you start putting, and they put a little bit of a head on it now because they realize that they need a little bit of something. But again, they're trying to make sure it's just alien enough that you'll say, okay, it's a coworker and nothing more.
Right.
I actually love their solution for the head too. I thought it was that great middle ground. Yeah, it's still approachable, but it can probably let you know not to get near it. So.
Yes. And it's not some weird gimmicky thing where they put some screen with
LiDAR,
funny
right?
emojis on it.
Yeah, it's the LiDAR.
Well, that one, but they have now another solution that's a little bit different.
Okay.
That one's a little bit more like the day the Earth stood still kind of thing.
Right. Oh, they should start calling it Gort. So
right. Now, the interesting thing here is this robot is called Digit.
Yes.
And why do you think it's called Digit?
Well, you could explain because this is not the right video. This isn't the one where they actually talk about that, but go for it. Say it.
Right. But I mean, you think it's like, it's Digit because it's digital. It's something to do with the computers. And it's like, well, you're kind of on there, but remember what's the etymology of digit in the first place? Digit means your fingers and toes. So, and it's because we count on our digits that we talk about things, having numbers, having digits, and then digital and everything else. But it has absolutely nothing to do with it from the computer standpoint, but it does have a little bit to do with the digits on our hands. And that is the walking structure that we see down there that we're going to look at it, what you call it, like the chicken legs.
Yeah.
That is something called a mammal that walks primarily on its toes is called a digitigrade.
Right.
Okay. Because it's walking on the digits, whereas a mammal that walks on its heels is called a plantigrade. So basically, now walking on your heels is just another way of saying walking on your ankles. And you think this thing's knees are backwards. Stop it right there.
Yeah, that's what I was trying to find was that particular.
Its knees are not backwards. Now, the thing that you think are its feet are not its feet. Those are its toes.
The toes. Right.
Okay. The thing that you think is the backwards knee is its ankle.
Right. And
the thing that you think is the hip.
For people who are thinking this is weird, if you have a dog or a cat at home, all you do is look at their hind legs, and that's exactly how they walk.
That's exactly what it is. And what you think is the hip up there is actually the knee. Now, what happens in evolution is that you think that you end up having some sort of mutation that causes someone's legs or knees to go from being posterior versus anterior. And no, it has nothing to do with that. It has everything to do with bone structure and the bone structure changing. So in our feet, we actually have the toe box and we have the joint there that's articulating. If you take that toe box and lengthen it a little bit, now you get that slightly bigger pad down there. Now, if you take your foot bone and make it really long going back, well, now suddenly your ankle is pointing way back and you're going to want to put it up there. And then if you take your upper leg, you take your femur and make it really, really short.
Yeah.
Well, there you go. So all evolution has to do is not actually change the configuration at all. All it does is change the lengths a little bit, and it's a slightly different structure. So in many ways, I would say that is very human. It's just the lengths are a bit different. That's it.
So, and again, just for people who are looking at this, the little white and black sort of oval looking thing, that would be the femur. So it's been shrunk way down.
Yes, exactly.
And then the tibia and fibula, is that the right ones? Anyway, those guys, your calf has been extended, and then your foot, the first part of the foot.
That's your foot right there. That's your foot bone right there. What looks like the lower limb.
Right.
And then the foot pads there are really your toe box or your toes. Yeah. And those are that means you're walking on your digits.
And then, of course,
so that's where the name comes from. And I love the fact that they decided to go with that name because I learned something just from the name.
Yeah, exactly. And also, you notice that the linkage that goes down to the ankle here is very, very offset. And I'm sure Gary wants to talk about that. Yeah.
Yeah. I was just going to say, it's interesting to see that their way they came to this design. I mean, a couple of interesting things and someone might have solved this by now. I think when I was reading about this like 5 years ago, the common literature was that they didn't know the reason why ostriches have 4 kneecaps or 2 on each leg. But ostriches actually have 2 kneecaps. I think one is similar in ours morphology, and it helps with basically distributing load across the extensor muscles. And then the other one is a fixed kneecap, and I forget the reason why, but they have two, and it helps kind of distribute load in their high-speed running. And the other thing I think they have is a really massive connective tissue advantage. And there's a guy, Lance Brooks, Locomotion, going to talk about ostrich running a hell of a lot better than I can. He's got some interesting videos, but they've got some fantastic connective tissue that allows them to reach those top speeds and allows them to remain elastic even at those really long lever lengths of the calf or Achilles complex, whatever you want to call it there. And so, yeah, I don't know. I think it's badass for what its job is, which is it probably has to move forward and back most of the time. It has to be able to do that pretty damn well, and then also being able to reach up and down very well. I think that the legs accomplish that probably better than even Optimus would. Right. There are some,
and if you look at this ostrich image, it looks an awful lot like Digit over here.
Right, right.
Yeah, you know,
and you know, I guess what I'm curious about is, Scott, do you know of any like what's the trade-off in that? Because everything has a trade-off, right? So obviously they've enhanced the walking probably speed, they've enhanced linear capabilities. They could probably really get a high power output out of this, if I had to imagine. But what do you think the trade-off is in going with this kind of leg design?
Well, there's a lot of nice advantages. First of all, the 4-bar mechanisms that you see on there, which are basically those parallelogram structures, they're used a lot in palletizing type of robots to make sure you're able to keep your outer structures parallel to the ground. So without any effort, without any sort of servo or motor, the linkage mechanism just kind of forces the feet to always remain parallel to the ground. Now, now, if I look at it, there are some actuators on there that I think they might lock or not need necessarily when it's walking on normal ground. And they almost use it to sort of change the configuration of the parallelogram structure to allow it to now take a different angle, because there are images of this walking on uneven ground and going up hills. And so it is able to compensate for that. And it's very clever. The other thing that's very nice about this design that we'll see is that it can get very compact and go down very low. So and when it wants to deliver a package, it's able to bend all the way down to bring that package to the ground without any effort, without bending its back. It's all in the legs. And at the same time, those legs can get very tall. So if it wants to, it can get up really high if it has to grab something up on a high shelf. So there's a lot of things about this design that are just absolutely great. And of course, we haven't even talked about the hips and what you're able to do in the hips as well. Right. So you see right there, they're able to change that back parallelogram with a servo. But if you then lock it, now you've kind of got that height structure. And as it moves, the mechanism almost works perfectly because the parallelograms back there will do the coordination of the movement of the other linkages in the kind of the way that you want to make sure everything stays horizontal to the ground.
And if you look at this, it's also, it would be a great jumper probably too. but I mean, the fact of when you think about if you have to pick up a big box in front of you, you have to not only squat, but you have to like spread your knees out. And it's very awkward to pick up a heavy, big object in front of you. This gets rid of that problem because
it's rid of it. Yes, exactly. And then you've got it also as like a counterbalance for when you actually grab the box and now have to go up. So there's just so many things about this design that are absolutely great.
I would think one big negative would be a balance issue because you're walking forwards and the legs are pointing backwards, which means it's much more difficult to keep your balance walking forward, or certainly like running would be. Although obviously ostriches do it quite well.
It seems to work pretty well. And there's also a couple of other degrees of freedom there in the hip that you don't notice that I think, Gary, you notice that it's there, that you have that rotation. And I think a little bit of abduction as well.
Yeah, I was going to say what I find interesting about this design and it being a robot, being, they can obviously change a hell of a lot more at a faster pace. Like the trade-off usually in a terrestrial locomotion for avian species. So like an ostrich that's running on land, or even the smaller birds or something like that, when you see them running after prey. And I believe in other digitigrade animals as well as lateral motion. So like if it needs to make a really quick sideways motion with a lot of power, it tends to be more difficult. And I think the running paths tend to follow kind of a curve or an arch for animals. I guess I could be wrong on that, but I believe so. So yeah, I would imagine that lateral motion would take a hit with something like this form of leg design. However, I will say they
Sorry about
they
that.
did add.
Sorry, folks.
It seems like they did add capability of hip abduction or seeing those hips go out to the side. So it's almost like a combination of some hip anatomy from a human and the sagittal plane motion from an ostrich. It's really fascinating.
We're doing this in real time, but I mean, you can see that motion is actually quite elegant.
Mm-hmm.
It looks very smooth. It's not when you look at digit walking, it's a little bit, kind of boing, 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 boing as it goes along, but it's still figuring it out. But
yeah, it's actually very good. And then there's the other aspects when we go up from the hip to the solutions that they had with the arm. And I think, Gary, you were also a little bit excited about something you saw there. I pointed out. I mean, the first thing we're going to say is that I love the fact they didn't worry about the hands. I mean, even though it's called digit, it doesn't have any fingers on the hands. They just have 2 degrees of freedom. Right.
Yeah.
They basically have a very simple wrist, and they do have some attachments they can put on the wrist if you need for being able to grab certain kinds of objects that just make it maybe a little bit more sticky or something like that. Some very soft things to non-slip kind of pads on there. So they have a wrist that's able to roll and it's able to pitch, but they're not worrying about the yaw. So remember, we had that big discussion. And they're not worrying about the fingers or anything right now, because for the applications they have it for, you don't need it. So don't worry about it now. That simplifies a lot. And then there's the arms themselves. And Gary, you want to get into that?
We're talking scapula here, because it looks like there's a little bit of motion up top.
Yeah, this is a pretty good view of that, because it's very,
yes.
Is that a vertically oriented electric motor that basically allows like almost like rotation about a vertical axis that brings it forward, or is there something even more there?
Well, what they've done is that usually you have 3 degrees of rotation in your shoulder joint.
Right.
And the way Optimus and a lot of others do it is that, if you're walking forward, and we call that your x-axis, and then your lateral axis, this way your y, and then of course your vertical on the z. Optimus rotates in the y, then the x, and then the z along the arm. So that's the order of rotation. They've done it different. They rotate an x and then y and then z. Now, in the end, that means you can still get the same orientations, but just with a different combination of angles. But what it does is it kind of allows that arm to go up. And the other thing is that Optimus, if you take all the axes of rotation and you extend those lines, they will all intersect at a common point. So it's kind of a spherical joint that way. Here, they do not. So the first axis and the second axis have a common point, and the second and third, but the first and the third axes do not. And they also have also a little bit of an angular offset there. If you look at the rotation along the roll of the arm, and then what is up there, see, that might not even be perpendicular to it. I'm trying to see if it even looks like it might be perpendicular. That's more of an illusion, the way it comes around, but just the way they shaped the whole arm rather than being straight from there, that they curved it. So I think they still have all the rotations kind of orthogonal to each other, but they just mixed up the orientation. And by mixing up the orientation, they gave you what you said you would like to see in a humanoid model, and that is a kind of a scapula. Yeah.
Yep.
Right.
Yeah, I'm curious. I don't know if it's the throwing scapula that we want to see just yet, but I think it's probably the best attempt for integration of a gimbal lock prevention mechanism of a shoulder joint.
Right. Yes.
For folks, can you explain gimbal lock for folks? Just quickly, really fast, nutshell.
Oh man, I was going to say, I feel like Scott at this point could probably give a much better description of gimbal lock than I can, coming from both robotics and
it's kind of a singularity mathematically, but
mathematically is a singularity. So pretty much
a degree of freedom, pretty much, right? Is the easiest way to put it. Yeah.
Yeah. What ends up happening is that you have 3 different axes of rotation that are orthogonal to each other, but as you rotate some of the first 2, you can force the third one to accidentally line up with the first one. So there's a position where you have 2 axes of rotation that are deadlocked along each other, which means if you need to get a rotation this way, well, which rotational axis should I use? This one or that one, or a combination thereof? And it also means as you go through there, the velocity profiles you have for certain things just start to shoot off to the moon. You start getting some of these divide by zeros and everything that can cause the whole mechanism to really spin wildly out of control. So almost think of it being like a whirlpool, that if you're far from the whirlpool with a canoe, you can get around it all right. But as you get really close to it, you get spun around really fast and maybe go down there. So mathematically, it's kind of one of those things. So it's you want to avoid it. So there are some positions of your arm, and in biomechanics that's known as Codman's paradox. But in robotics, we just call it, oh, that's the polar singularity. So
Right.
once again, the biomechanics have to come up with these weird names rather than yaw, pitch, roll. They got to do this pronate, supinate.
The biomechanics have been
else.
around a lot longer than the roboticists. So. but I mean,
we've got to add like 6 layers of abstraction to everything just in case, just to make things a little bit hard. Yeah.
It's kind of a control authority thing, honestly. When you start getting two of the axes too close to each other, it loses the control authority to separate them back out again.
You can think of it that way.
Like you said, the whirlpool that's spinning.
It's like you lose your lever arm,
Yeah,
it's like,
exactly.
If you have something at 90 degrees, it's a lot easier, but once something lines up, suddenly you don't have that mechanical advantage anymore.
Yeah. All right. So yeah, I mean, he's got, really interesting arms. It's very fascinating as they talk about through this video. They're like, we started with a blank sheet of paper and designed this thing, and this is what we ended up with. And because it's working in a human environment, it obviously has to, it can't be this tall or something, right? It's got to have some dimensionality that's similar to humans, but they came up with a more or less human looking robot, which is why human-centric, works with humans, not humanoid, intentionally designed. You could argue that Optimus is more humanoid because they have 5 fingers, they have a head, right? Yeah. They intentionally,
it was intentionally designed to have the humanoid form factor. Exactly. So they came at it from completely different design criteria and approaches, and have come up with something that's very, very similar.
So do we see the full circle then of them saying, we're going to first principles this, we're just going to see if we can build the most effective thing possible, and then eventually we just end up with a humanoid robot because we just, it turns out that seems to be the best thing. You think that is the best thing?
Well, yeah, and part of it is because, again, being human-centric means it has to be able to work in the human world.
Right.
So if it was designed to live in a different environment, they probably would have come up with a completely different form. But that's part of what kind of guided it that way.
Yeah.
But still, I really like the design principles.
If it was designed to work in the ocean, it would probably look a lot more like a dolphin or a shark. It would just be natural that it would have to look like something like that. So
exactly. Or if it was supposed to work, live in trees or something like that, it would also be very different.
Yeah. Right. Do you consider something like Spot?
Like that.
Do you consider something like Spot then human-centric if it works in human environments but doesn't take human form, out of curiosity?
I'm not the one that coined the term. Well, let's ask them.
Yeah.
So, John, invite them on the show. Okay?
There we go. I have a feeling anyone probably come on. So let's have them. Let's have them.
Please come on. Yes.
Come on for a chat. Come join us.
It's a very friendly environment here.
I think Spot. That it's just hard to know because it depends on what they started out to do. Did they go like, do we clean sheet this? Or did they say, we want something that looks kind of like a dog? And what would we do to make it look like that? It just depends on how they started off the whole project.
Right.
Well, are dogs human-centric? I guess you have to answer that question first.
Yeah.
They live amongst humans.
Yeah.
They're able to survive in our environment without any problem. And it was designed to go into hazardous and dangerous areas for inspection anyways.
Right.
So that's why it was such a good form.
Well, and it has a huge advantage, which is that it doesn't have balance issues because it's got 4 legs instead of 2. So, there's a pretty solid argument for making something 4-legged rather than 2-legged because it's very, very unstable.
Question from the footage from you guys, did you see anything that would indicate what they're doing for training that might be differently than anyone else in the industry, or do you think they're taking a similar approach? It didn't look quite as smooth yet. The coordination and stuff looked more like early Optimus, and definitely, interestingly enough, with the digit legs, I know, Scott, before we were talking about lateral perturbations from Optimus, but I think I was almost seeing more forward and back from the digit legs in a couple of videos I saw, but I don't know what you guys, if you guys noticed anything like that.
Yeah, I mean, you do see that they do have a little bit of
right here. You could actually see it spread its legs apart.
Spread its legs a little bit. So it has all the motion that it needs. So it seems to have sufficient degrees of freedom. And it's interesting. It doesn't have such a big booty.
Right.
It's very interesting that compared to the way Optimus has been set up.
Mm-hmm.
But I mean, clearly the biggest motors are right in this area. Just some of them have been offset into the femur itself. Because there's a couple of them right there.
And somewhere there's a YouTube. I didn't have a chance to look at it today, but there is something out there about powering up Digit and I guess giving it a task or something like that. So I have to look at that to understand it. And somewhere around there, I'm trying to see where the on-off button was.
Is there
I'm
one?
sure there is. There probably is one. I'm sure there'd have to be.
Well, here, this is
is
actually a
that
good
it?
close up. So it has
Like
computer
camera.
vision. It has LiDAR
Could
on
be.
top. And then obviously, a downward looking cameras and a forward looking
Vision, right.
camera.
Yeah.
Hmm.
And so with the LiDAR, I think they're probably using something like SLAM to help them with the navigation.
Right.
And then they have their own control system on top of that to give it the task to go ahead.
These are actually these are climbing slings attached to it. That's Dyneema climbing slings. I just recognized that from my other world of climbing. I was like, wait a second. I recognize that stuff. I have some of those in the garage right now.
Yeah.
It's going to go climbing next.
I guess so. It'll be the climbing robot. It's going to need
And it's going to be interesting to see where they get their actuators from, whether they were able to buy them off the shelf.
Right.
Because
Or if they made them in
Tesla
them.
says that they couldn't, or whether they also have kind of their own bespoke servos.
This also, I think, shows very, very clearly the offset of the shoulder. Because you got the one axis that's right here, and then the other axis way back here. So it's significantly offset.
Yeah, which is kind of those are some of the design, and I would say that constraints or trade-offs that you would have when you do something like that, because a lot of times everyone would like to compress it together because our shoulders and everything, we don't offset like that in our torso. It fits in there really neatly, but it doesn't have to be a human. They just need to get the arms that are out there, and that probably is good enough. So it's not a bad solution, which is why they went that way.
I think you said also for a cobot, for something that's supposed to not have pinch points and stuff, that makes sense because you don't have an area like this that you could compress. And
that's why they have those offsets. You also look in the elbow. Is some cobots, they actually do have an offset between the upper and lower arm to get around there to kind of avoid those pinch points. They designed it a little bit different. That they do have a mechanism in there that kind of rotates to make sure everything is in line. Yet there is a lot of space in there, and I'm sure that they have like a limit that you can't go too far. So it does not look like you can get your finger in there and get it caught. There's no way.
So you can see that it is offset a little bit, it looks like, but also there's probably just.
But if you get from the back view, it kind of there's a nice plane that everything lies in. It looks like there's an offset, but it's not as bad as you would think.
Yeah.
There's a little bit there. I mean, you see it on the universal robots that they have a much bigger offset in there, but they make sure that you can't get your hands caught in there. And again, here they are going on an uneven surface. They're able to do that quite well. And I think we see a little bit of rotation in there. I don't know if we see.
Yeah, let me see if I can do it in motion here so we can actually.
Are you able to slow this down at all?
You can. Hold on. Let me put this on. Play back. I usually play everything back.
That's a decent gate too. I assume that's real time. So that's not a bad gate.
But I was noticing also, very interestingly, you could actually see the flexion in the upper part of the leg as it would hit uneven surfaces. So very cool. Let me see if I can get it right at the beginning. Okay, so this is quarter speed. But you can see, as it hits uneven ground, the leg.
Oh, yeah.
That's really cool. It's unfortunate there's those lens flares going through there.
Oh, yeah. So it's doing a little bit of that just to kind of deal with the balance issues.
Yeah, like right there, you could see that the right leg on that thing, jiggled as it was going. So that was actually very cool. That's what these guys get for putting anything online, because we can break it down like frame by frame. But yeah, that right leg, it has like a whole thing that it goes through right there, which is very cool. Like this leg, it hits. I think the next step, it hits some really uneven ground, like that, and it really has to kind of adjust and twist. So that was very cool because you could see it twisting and I don't know. Sorry, I don't know what the correct term from biometrics.
No, the rotational adjustments and stuff. It's definitely very interesting.
Yeah.
It's funny. It's almost in a couple of months. Like, is that knee cave inward? I'm almost like anthropomorphizing it, being like, oh, this guy's got valgus. He needs to watch his MCL or something like that, and is always going up that that hill there. But then I have to snap myself.
Are you going to teach it to run better? It's like you got to learn how to run better.
Get Optimus in on an instrumented treadmill with some motion capture and just see what happens. Run a combine style test on it. Yeah.
Are you? You should do. Honestly, that'd be pretty cool to watch Digit do that too. Like to watch, especially as you took the treadmill and started like doing different angles and stuff. So it had to like deal with that would be really awesome.
Yeah, so, I definitely wonder seeing the seeing the lateral motion, the hip abduction and digit is really interesting. And I'm curious to see if that becomes something they keep long-term, if that's added functionality for stability, or if that ends up being a hindrance somehow. If they could have maybe, because if you look at even going back to digitigrades like the ostrich, for instance, the pelvis is way different on an ostrich than what we're dealing with, right? It's much higher up, and I believe it doesn't allow for as much lateral motion, and it's generally for a reason. So I'm curious to see if maybe they lose too much stability by trying to give it an extra degree of freedom in that lateral plane when for its purpose it may not fit in the way that it seems to fit in Optimus.
Is ostriches also, if I'm remembering correctly, their pelvis is very wide compared to their body, right? So their legs are really far apart. So they get some stability just from the fact that their legs aren't very close together. So
whereas, and that's interesting you brought that up too, because looking at Digit 2 walk up that hill, that the hip joint center, you could say, the center axis of that hip joint, or the amalgamation of the hip joint, does look rather medial, pretty close to the midline there. Like it doesn't have a whole lot of support.
Yeah, I'm looking at one. I guess I can just to show what I was looking at here, just so you can see, because you could, like, this is there's a good separation like between the legs from that view. So and ostrich, I guess, well, I don't know, I was thinking ostriches are all legs, but they have really long necks, so they have just like they're like two little stalks, a big ball, and then one stalk that sticks up. So there's like, I guess the center of mass is still right there in the middle.
And that, mace, that mass on the end of a kinetic chain there is pretty helpful at that high-speed balance. That's one thing I think that going with a digitigrade lower body without some kind of extending counterweight may prove kind of difficult at higher velocities. So even if maybe the lower limbs are really well designed to try and pick up maybe faster speeds or more power or something, or more complex challenges, if it doesn't have that help as a counterbalance, maybe it becomes not as beneficial when they try and increase performance out of it. Not sure.
Yeah. And then it's just a question of, do they want that additional performance?
Right.
It depends on what the use case is. And, their use case maybe also is like only under 5 miles per hour. We don't want to be running with packages. You're not allowed to run to the factory floor. You're not allowed to run around the swimming pool, like all those things. So if you look at it from those use cases,
All right, now I just want TrackBot now. I want to see one of beat Usain Bolt. Like,
Speaking Boston Dynamics will figure it out.
But they started with that, what did they call the original one that had the multiple linkages? It was like just a mass spring. I can't remember the name of it, but it was very cool. Just sort of walked in. I don't have the video. I can't remember where it was, but it was
the original Boston Dynamics.
No, the original one that Oregon State University did before they spun it off as
right. Yes. And that was interesting. That's what they learned a lot about stability. And then it's almost like they had two legs coming in. So they had a 4-bar mechanism that went out and came in. It was more of a scissors kind of joint. And that was rather interesting. And then they kept on evolving that because they were really thinking about walking and nothing else. We want to solve the walking problem. And they've come up with some pretty nice solutions, there's no doubt.
Yeah. I noticed on Digit that they didn't all of the rotation of the upper or the arm is accomplished at the upper arm area, wherever the humerus. Do you think that's a good call for everything that they need to kind of do long term, or what they're hoping to do long term? No hands, no rotation at the wrist.
I think so. Yeah. So that little kinematic offset they have up there.
Yeah.
It's okay. It's like when you try to do the math to solve these things, you want to get rid of all these offsets and have everything line up. It makes the math a lot easier. And some offsets will actually make it impossible to come up with an analytical solution. You have to do a numerical one. The one they have up there, doesn't throw that off. And they don't really have anyone at the elbow, so that's all right. And they don't have any at the wrist. And usually it's the one at the wrist that causes the kinematicians like the fits on trying to solve that. But you really don't want an offset at the wrist because that's what's trying to get into things. And you put an offset in there, suddenly your wrist becomes really bulky and hard. So when I see it in a lot of robot models, I'm like, why are they putting it in there? It's like not only making my life hard trying to solve this thing, but I would think mechanically, it's sometimes just easier to mechanically to build it with all these offsets, and you don't realize, but now what about accessibility? So they've made sure everything goes back there, and you do get a little bit of that yawing because you really do have a 6 degree of freedom arm, except it's all back here. And there are ways of using the redundancy around that elbow joint, which is, we think of it as like a redundancy about the elbow. It's really the third axis that you have up on the shoulder allows you to do it. And you can see they have everything because they work in this plane quite well, but it can also do this. So you'll see that has these actions. So it's got more than enough mobility. And when it comes to picking up a box, if I'm picking up any box, it doesn't really matter whether my hand is on here like this or this or this. That's all the yawing is going to do, is say that you've got to do it. The only reason it would be is that my hand has to go through some weird slot or something like that. But I could probably do that with some shoulder roll if need be, to be able to get that in there. So if you're just grabbing something, all you care is it's like that. And then you just make whatever accommodations you need to make when you put it down on the ground. So I don't think they're limiting themselves at all for the application space that they're looking at.
Apparently we're sponsored by Kleenex too. So
yeah, evidently. Some people might argue it's like if you get like a drill bit or something in there and you've got to get an axis in a particular way or something like that, that maybe you need that extra hand motion. But that's not what it's designed to do. It's designed, as you can see, to do a lot of these kind of pick and place operations where it doesn't matter exactly where you grab something, just as long as you're able to do it. And they don't need that much pressure in their hands. You'll notice the arm, because the arms can do this kind of motion, they can get a lot of pressure on the hands to make sure they have a good grip on that box and move it around. So I do not really see any major flaws in their design. I think it's really quite good. And I wouldn't be surprised if eventually they figure out how to put a hand on there that maybe has a couple of digits. I don't know.
Yeah.
No pun intended, whether it decides to have an opposing thumb or something else or some kind of gripper. But it's like you said, it's a kind of a Lego hand. So if it's a Lego hand, it means you're able to snap something on there.
Yeah.
The only problem with that is a lot of times when you get that hand, now you've got to run your services through there. And you see they did a really good, and it's like, I think in the wrist, it looks like they've got a built-in servo in the wrist. When we saw the typing that was going on, you see it could go up. Yeah. I'm trying to figure out how they're actuating that. And I think they have probably a tiny servo in there, but servos require power. And to get power, you need wires. And they've done a really good job of concealing all the harnessing and wires. Whereas, Optimus, we can see it's still way out there. We're trying to figure out, man, are they ever going to be able to hide that stuff? Is it going to get snagged on things as you're going around? Right. So again, they may have put a lot of thought, and some people have asked me, what would you do different with Optimus? And I've got some ideas, and one of them is figuring out, better ways of hiding the wiring and the services they need to have going through there that might require, some changes to a few things.
Cool. I just popped up a video. This is the Optimus one, just because we haven't shown this today, but as a comparison to the way that the Digit walks when we get to the walking part here in just a second.
Right. And you can see all the wires are just kind of hanging out that are necessary, partly in order to actuate the hands. You need to have some sort of power going into those
that
servos.
Little turning motion there is very cool.
Yes.
Closing the hips in on each other. Yeah.
Yeah.
Mm-hmm.
And also there's a couple of really finite adjustments you can see in the hand as it's starting to grab the arm. It's just beautiful to watch.
Right. Yeah, that little adjustment, but that motion right there where it knock knees is very cool as a way of.
That's what's needed to pivot.
Right. Yeah. Now, the walking motion of this is quite different than Digit in the sense that it is plotting, I guess. It seems to be like Digit's kind of walking relatively rapidly, which is probably a compensation because it's probably easier to balance if it keeps moving.
I was going to,
Optimus is taking the opposite tactic, which is very slowly and carefully planting its feet.
A Digit would win a foot race at this point. Digit is very confident in its movement and how it goes. Yeah.
But I think, am I wrong about that, Gary? Is that correct that the walking motion, that oftentimes that little just continuing step?
I was going to say, I'm not sure I would describe Digit as more confident in its walk yet. It might be getting a foot race just from output and maybe the limitations of the programming right now. But I would have concerns over things like balance, like we talked about, and also that the small, like you had mentioned, John, the small feet to me looked more like someone concerned about balance than something that was powerfully walking quickly. I think the only example I can come to mind is probably just because my girlfriend and I were talking about this not long ago, but the foot-bound walk. Like if you go in and even some type of traditional Asian theaters and stuff like that, even Vietnamese theater from stuff my family and I used to go to, the walk is really small and it's very slow paced with lots of little steps, and it generally becomes because there's not a whole lot of surface area at the foot when it lands. thus providing not a whole lot of balance, and you have to take more steps to keep maintaining that balance.
For like a Western tradition, also like a ballerina that walks on her toes, like that same thing where you have to like continuously move because it's so difficult to so many stresses, and it's so difficult to balance on just your toes. So
it's the thing is, as far as balance, it's easy to stand and it's easy to keep balance when you're moving. But it's sort of the twilight zone in between the two that's a bit hard. Is that getting that transition of going from standing to moving is usually where you'll get some sort of toppling. But the same with a bike. You know, if you go really slow on the bike, you fall over. It's just, there's not, you got to get a certain amount of speed. You get that momentum going, and then you can have that very confident.
I think that's a major reason why it's so difficult for children to learn how to ride a bike, because there's a commitment the hardest part is the first part as you just start up, and then it's easy after that. So,
exactly. It's always getting started. It's definitely the hard part.
So cool. Other thoughts about this? I mean, I think this is really, I love to look at the variety of different solutions that are coming online. And I was looking for the other video. I couldn't find it, but there is another Agility Robotics video where they actually show some of the vision systems, and they're clearly using LiDAR, and they've got a 3D map of the environment, and you can see it walking through there and everything. So it's obviously not dumb. It's able to see what's going on and somehow target like boxes and know what to pick up and everything. So
I'd be interested to know how they're doing that for sure.
Anyway, I guess we'll just invite anybody from Agility Robotics that wants to come on the show sometime and talk to us. We'll be happy to have you. So.
More than happy. Yes.
For a live demo, hopefully.
Any final thoughts or anything? Gosh, we've been going for like an hour and 15 minutes or so. So
I did have one actually just about the hand, going back. The Lego hand. I'm wondering, do either of you guys have any insight as to why they went with that design necessarily? You know, like for something so small, it seems like why go through the trouble of actually putting a hand at all versus just the flat part and closing it at the shoulders for just that little bit of functionality.
Yeah, I'm kind of wondering, because it looks like in some earlier designs it didn't even have that. So like say you just could
like
able to come in, and it might be because they're thinking of having some sort of attachment on there. So maybe you really do clip something on there, and now maybe it gives you some other functionality that you wouldn't normally have, and you need to have a little bit of that kind of flippering movement back and forth. But we'll ask them when they come on.
There we go. Come on, guys.
Why did you see the need for a wrist?
Did you see any lateral motion at the ankles at all too? It seems like it looks like there's a hinge side to side at the ankle attachment there, but I couldn't see.
I'm not sure. I have to look closer. I thought it was just kind of the normal pitching motion. I don't think.
Here's
that's a good question. We'd have to look at it. So
this is a schematic of it, and it looks like it's just got a passively compliant joint down there at the bottom.
Yeah.
Like that little sort of horseshoe shaped thing. Maybe it just kind of, it's got a spring loaded, so it tries to stay still, but if it needs to maneuver slightly, I don't know.
It's got 2 bars on that midfoot, if you want to call it that, the plantar fascia.
Yeah. Huh.
For lack of a robotics term on that.
Good questions.
Yeah, so you're not going to get any twisting motion on that. Yeah.
But, I think it's awesome, though. Yeah, overall, I'd love to see it. You talked about climbing. I'd love to see it throw some real nuts for feet on there, and then use the hook hands to just see how fast it can get up the wall. Yeah,
we'll just give it like Captain Hook. We'll just give it. Put some climbing shoes on the toes, and we're ready to go. It would have a huge advantage over humans, which is it doesn't have to deal with its knees. One of the problems with climbing is that your knees are always, you're having to splay your feet out or turn them in or do weird things because they're always right into the, the rock.
Yeah.
So, let's not talk about the drop knee maneuver.
Yeah. Okay. We'll not talk about and femurs.
Sensitive topic.
Femurs. Good. I actually just was sending messages on Twitter to Ellie this morning, and she seems to be doing great. So yeah.
She just sent me a video showing that she was able to get up from the floor pretty much unassisted, without crutches or anything else. So she was down doing, I think, some yoga or some stretching or something down there, and get up. I'm like, holy cow, really? So
nothing like being young. You recover fast.
Yeah. Well, and active. I will say it helps. Yeah, we see it here too. Just the better you set yourself up prior to going into one of those injuries, the better off you tend to be coming out of it. It's really interesting.
So everybody planning on getting an injury, just make sure you set up properly before.
Right, exactly. For when you really want to break your leg. Yeah.
and certain amount of determination. Yeah. And
absolutely.
She needs to make sure she's healthy enough for the launch. So it's like,
I know.
Yeah.
That's good motivation. So
really
Scott, you're going to the launch, correct?
I'm hoping so, depending upon when it is.
Gary, are you going? Because you're in Colorado. It's not that far away.
I wish. Yeah, no, it depends where it is. I'll be in, is the launch, I forget, out of Florida or Boca Chica?
Boca Chica.
So I'll be in Houston in 2 weeks. I want to say there's an astronaut human health and performance summit. So I'm like, if it lines up, it's not far from it. We'll see. But right now, it doesn't look like it. I wish. Yeah.
I think right now everyone's thinking it's the earliest is the 17th. What I saw, I'm trying to think who tweeted that out. That next week is just going to be the wet dress rehearsal.
Right.
With the earliest launch attempt, probably.
I don't even know about a static fire.
I don't think there's going to be a static fire. No, I don't think so. But they may load propellant on and off and just check out all the systems, make sure it's all right. And then the 17th might be the earliest first launch attempt. And then I think it was Zach Golden said that if for some reason they try to launch on the 17th and if it's scrubbed, which then means they have to get rid of everything, your next attempt is about 3 days away because then they have to truck in all the methane again. So
that's right. It is an awful lot of methane.
Right. So it's not like, we scrub today, we'll go tomorrow. It's like, you have to hang around a couple more days.
I'll have to drag Ellie out here too to get some motion capture done on her before she starts physical therapy. I'm meaning to reach out to her about that.
That would be pretty cool. So you want to like baseline it or something? Or...
Yeah, well, I wish we had a baseline. I asked her before she had the injury. We just never got a chance to get her out here. So we missed our window for a baseline, unfortunately. She has a new baseline. But it'd be interesting to at least give her her current baseline data, and then she can use that for physical therapy or whatever from there. So
that'd be super cool.
Yeah.
All righty, folks. Well, it is getting close to dinner time, so I will let you all go. Well, maybe not for you quite yet, Gary, but anyway, thank you so much for spending all the time this afternoon. This is a great conversation. And of course, I'm sure people will have questions, so leave them in the comments and we can do another video, maybe with the folks from Agility Robotics, and we can answer some of the questions. That would be awesome. All right. Thank you all so much. Have a great day. Bye-bye.